Okay, so in this particular video, I'll show you how to attack a position time graph that's for a uniform accelerated object to the right. So here we have a motorcycle accelerate uniformly, which is just constant from rest. That implies that its initial velocity is 0. And then it says here the schematic shows so, and then the position time graph that corresponds to the motion is given. All right. So it says here, if the motorcycle's position at time equal to 0 is 0, which is indicated in the diagram here. So the diagram is pretty helpful here. It says xi is equal to 0, vi is equal to 0, and then at some time later, at 5 seconds, it is located at a position of 25 meters. And that value is given in the graph. So if you look at the graph here, there are a couple of points given to us here. At 5 seconds, the position is at 25. Because this is a position versus time graph. So the first value is your time in the coordinate system. And then the second value here, 25, is your position, aka x of t. And then it gives us that at 10 seconds, and the object is located at 100 meters. Okay? All right, so here are the different parts, A, B, C, D, E, F, G. Let's go ahead and do it. The do part A, it wants us to find the distance from 4 to 10 seconds. Which is not bad. All right, so here in the graph, here is 4 seconds. Watch where my cursor is going back and forth. There's 4 seconds. I don't know where that motorcycle is at 4 seconds, but I can find it out. And then I know exactly at 10 seconds, it's at 100. So what I can do is I can find the distance that it traveled during the first 4 seconds and then subtract it from the total distance that it covered during the first 10 seconds, which is 100, and I can find the gap. All right, so keep up with the stuff that comes up on the screen. Here, I want to start at 4 seconds, and I know I got to go all the way to 10 seconds. And then this is what the question is asking for. The question is asking for how long is this vertical arrow, aka your distance travel. Okay, so, well, like I said, I don't know where the object is at 4 seconds, but what I can do is I can find how far the motorcycle has traveled during the first 4 seconds. So watch my cursor. As it starts to accelerate, it'll get up to some position, and this dot here at 4 seconds, if you go left, it doesn't intersect the one of the points on the number line nicely, so I can't just make an assumption what this value is. I actually have to find it. Okay, so here I can just use the displacement function. I'm going to start at 0 though, so you have to listen to well here. I'm going to start at 0 seconds. At 0 second, my initial velocity is 0. It is stated in the problem that it starts from rest. So I can cross out the VIT term. Okay. Well, delta x is simply xf minus xi if you break it apart. But xi in this case is also 0 because it said so. It says that at time is equal to 0, its initial position is at 0. Okay. So for this one, it's a little easier to do because xi is 0, so we can just cross that out. Don't always just assume xi is 0. You got to read problems and you got to look at graphs correctly. This one, the graph shows that it starts at 0 and the wording says that it starts at 0. All right, so here to find xf at 4 seconds. So again, you got to find this length here where I'm tracing it. From 0 seconds, it's at 0. At 4 seconds, it has traveled a certain amount of distance, but I don't know what that distance is on the graph. Anyway, I know it's between 10 and 20, but I got to find it. Well, to find x of t, which is xf here, you can simply do 1/2 a t squared. T, I substitute it for 4 seconds because I'm starting from 0 and I'm going to 4. All right. Well, I don't know what a is, but that's okay. Because I don't know what a is, I can use the information given to me using one of the 2 points. Again, one of these 2 points is critical. I know at 5 seconds, it's at a position of 25. I also know at 10 seconds, it's at a position of 100. Here, I'm just going to go ahead and use the first point. Okay. So the first point is 5 seconds and 25 meters. So what I can do is I can use xf as 25 meters because it's given to me. And then I can plug in 1/2. Again, just carry down. A, I don't know what a is, so I need to find what a is because the graph shows that it's a parabola, parabolic function, quadratic function. So I know it's going to accelerate. Here, I've chosen to plug in 5 seconds because I'm using the first coordinate point that's given to me in the graph and in the schematic. So it says after 5 seconds, the object is at 25 meters. So it gives you enough information to find what a is. Okay. So if you watch my work, the only variable missing is your a, and therefore we can just crank out, algebra here. 5 squared is 25, and then If you notice here, the 25 on both sides will cancel out. So really to solve for a, you multiply both sides by 2 just to get rid of this 2 in the denominator. So therefore, if your math is good, your algebra is good, you get a is equal to 2 meters per second squared. And that's just a magnitude. We know it's accelerating to the right. So I know it's 2 meters per second square east, but the question is not asking for acceleration. So we just need the value to finish our calculation. Therefore, I can carry this work down. Now that I know what a is, I can plug a for here. Again, in the last statement, that's in red, xf is equal to 1/2 a for second square. I don't know what a is, but I just went and found it using the coordinate points that's given to me. Now that I know what a is, I can just substitute that in. So I just carry this work down. xf is equal to 1/2. A is now 2 meters per second square. And then 4 square is already 16. So I square that. And then the s squared just comes from squaring the unit as well. So the s squared here is going to cancel out with the s squared in the denominators, which leaves us with units of meters, which makes sense. All right. And then the 1/2 and the 2 is going to cancel out. And therefore, really the only answer left is 16 meters. So our xf is 16 meters, okay? So where is the object located at 4 seconds? Well, based on our work, it tells us that after 4 seconds, the object is located at 16 meters on the number line. But that's not our answer though, right? The question is looking for how far did it go from 4 to 10 seconds? Well, we know at 4 seconds, it's at 16. At 10 seconds, it's at 100. So all we gotta do is do a little basic subtraction. So to find the total distance covered, we would take 100 minus 16, and that would give us the distance of 84 meters covered between 4 to 10 seconds. So the answer is 84 meters, and distance is a scalar, so you don't need to include any sort of direction. All right, so here in my diagram, or relating to the graph, D is going to equal to 84, because if you watch my cursor, that would be 16. From 16 to 100, that would be 84, because 16 plus 84 is 100. All right, I hope that helps. If it doesn't, listen to it again. All right, let's do part B and C. Part B asks us to find the instantaneous velocity at 2 seconds. Part C asks us to find the instantaneous velocity at 8.5 seconds. These two parts are pretty straightforward. A v of t is just vf in our kinematics equation. So the easiest way to do that, I think, is just using vf, which is equal to at plus vi. This function comes from our average acceleration equation, and we can just rearrange the solve for vf. And if you have been practicing, this function should be in your back pocket. Vf is equal to a delta t plus vi. Well, it asks for vf. We know what a is. We know what vi is. It says at 2 seconds, so I'm just going to start my problem back at 0. At 0, my vi is 0, so I'm just going to cross that out. A we just found, which is 2 meters per second square. So therefore, all we have to do is plug and chug. A, I substituted 2 meters per second square. Delta t here is 2 seconds. Why? Because it wants us to find the velocity at 2 seconds. But I'm choosing to start from the interval from 0 to 2 seconds. So if I go all the way back from 0, my vi is 0, like I did cross out here. Okay. So therefore, vf is just 4 meters per second. And because it asks for instantaneous velocity, which is a vector, you should include the direction. In this case, the schematic shows the motorcycle going to the right. So I'm just going to say that is 4 meters per second east. All right, let's do part C. Again, part C asks us for the same thing really, except for at 8.5 seconds. By the way, this stuff that just came up on the screen, I'd like to point out that the slope of your tangent line is your instantaneous velocity. It's the tangent line. It only touches one point on the dot, and it touches at 2 seconds, and that slope there of that tangent line is 4 meters per second. So the instantaneous velocity is the tangent line that touches a single point. What point? The point of time that you're interested in. So here, that tangent line touches the point at 2 seconds, and it sets that the slope is 4 meters per second. So your instantaneous velocity is 4 meters per second, and again, positive ease, whatever you want to say. Let's do part C. Part C asks us to find the instantaneous velocity at 8.5 seconds. We can do the same process. I want to go back to 0. I want to start at 0. Why? Because it just makes my life easy. When I start at time equal to 0, I can cross out vi, because for this diagram, it says vi is equal to 0. Again, don't just cross vi out just because I'm doing it here. This problem said that vi is 0, so I can cross it out. If you run into a problem where vi is not 0, then just plug in whatever value vi is, okay? So we can just substitute in a again for 2 meters per second squared, because we calculated on part A. And then time here is 8.5 seconds, because I'm going from 0 to 8.5. And if we do that, we get a velocity of 17 meters per second. And here again, I've included the direction, which is east. Therefore, the tangent line at 8.5 seconds, which is roughly here on my graph. You know, this is between 8 to 10, so 8.5 is like right around there. I didn't put a dot. And the point is to teach you that a tangent line that touches a single point on a position time graph is your instantaneous velocity, okay? Not average, it's just a single point, so it's instantaneous, it's at that moment. So the slope of this tangent line here is 17 meters per second, which suggests that the object is speeding up. If you think about it, at 2 seconds, it is only moving at a rate of 4 meters per second, and the slope is getting steeper, which suggests that the object is speeding up. Therefore, it makes sense. This is 17 versus 4, okay? So the object speeding up, which makes sense in the schematic here as well. All right, let's do part D. Part D asks us to find the average velocity between 0 to 6 seconds. So here, the time bound is dictated from 0 to 6. So to do average velocity, we just apply the physics function of displacement over time. To do displacement, all we have to do is just do this. You apply the displacement function, and then here, delta t, I'll plug in 6 seconds. Hopefully you didn't get lost there. From 0 to 6 is just 6 seconds. So the only thing holding me back is my delta x. But to find delta x, I can just use my displacement function, vit plus 1/2 at squared. And because it starts at 0, I'm just going to go ahead and cross vi out. So vi just disappeared because at times equal to 0, vi is 0, so that vit term is kind of useless in this part. So delta x is simply 1/2 at squared. Well, I know a is 2 meters per second square. Here, time is 6 seconds from 0 to 6. All right. Therefore, all I have to do is substitute numbers in. A is 2, t is 6. Don't forget the square. And then if you are watching carefully, the 1/2 and the 2 for this particular problem is going to cancel out nicely. Okay. A just happens to be 2 for this one. So 1/2 times 2 is just 1. So really, 6 squared is just 36. So our displacement is 36 during the first 6 seconds. So delta x here is 36. Once we find that, we can just plug in for delta x. So therefore, I've carried v average down here. So v average is simply 36 meters divided by 6 seconds. Well, 36 divided by 6 is just 6. So the average velocity is 6 meters per second, and include the direction because velocity is a vector. So the average rate of increase here is just 6 meters per second in the forward direction or to the right. All right, and that would be your answer. Okay, graphically though, this is what it looks like. This one asks us to find average velocity between 0 to 6. So here the blue line, the dash came up, that's 6 seconds. Okay, and then vertically, you got to go up to that point which we just found. That's 36 meters. And then it's important that you understand what is that's calculated. It asks for average velocity, which it technically just asks you to find the slope between 2 points. Which 2 points? From 0 to 6 seconds. So this solid dash line is applied because we're asked to find average velocity in this case. So the slope of that line is simply 6 meters per second. Okay, so that's just an average. All right, letter D can be also calculated using this strategy. I like this second strategy more because I think it's quicker to do, on an assessment. It asks your average velocity between 0 to 6 seconds again. I like this strategy better. So hopefully you keep up with this one. If you like it, adopt it. Okay. Well, I know the average velocity, with constant acceleration can be calculated using Vf plus Vi over 2. Well, the time interval here is from 0 to 6. So I can run all these values pretty quick in my head. Hopefully quick in your head too, since the number for acceleration is nice. Vi, I'm going to cross out because at times equal to 0, the object's at rest, which implies that its initial velocity is 0. So if you can run all these bullet points quickly in your head, then apply the strategy. If you can't, don't use it, okay? Because it might backfire. At times equal to 0, it's at rest. At times equal to 1, acceleration is 2 meters per second square. Therefore, that tells you and me that the velocity changes by 2 meters per second every second. So from 0 to 1 is 1 second, but it changes by 2. Therefore, the velocity is going to go from 0 to 2, and then it's going to go from 2 to 4, and from 4 to 6, and then 6 to 8, and then 8 to 10, okay? And then 10 to 12. So, to me, the sequence is pretty easy to do. However, you just have to make sure you can zone in on values that you need. It asks from 0 to 6, so I'm just going to highlight 0, and I'm also going to highlight 6 seconds. Well, at 0 second, it's stationary. Hence, I cross out my VI in my work here. And then at 6 seconds, well, it's moving at a rate of 12 meters per second. So it's a quick plug and chug, but it can backfire if you can't find these instantaneous velocities correctly by interpreting A correctly. All right, so therefore VF is just 12 because at 6 seconds, the instantaneous velocity is at 12. And then again, VI is 0, so I just left that out. 12 divided by 2, which is 6. So as you can see, we arrive at the same conclusion simply by using our instantaneous velocities and then adding the two values that pertains to the time bounds and move on with your life, okay? So the answer is the same. So therefore the slope here is also 6 meters per second for the first 6 seconds. That's your average, okay? All right, let's do part E. E, same concept here except for the time is different. The time here is between 2 to 5. It's not bad, okay? Same strategy, average velocity is displacement over time. So here, my displacement, I don't know what it is, but I know that my time is 3 seconds because from 2 to 5 is 3 seconds. So if you kept up with the last strategy, use your displacement function to find delta x. But here, the time that's your starting point is 2 seconds, okay? So do not cross out VI out of habit. You always have to pay attention to the time. Here, the problem starts at 2 seconds and ends at 5. Well, at 2 seconds, the motorcycle is already moving, okay? Well, how fast is it moving at 2 seconds? If you need to go back to the previous slide, at 2 seconds, it's moving at a rate of 4 meters per second because it went from 0 to 2 meters per second to 4 meters per second. Okay, so that took a time of 2 seconds. So here, VI is 4 meters per second at 2 seconds. Time, well, it starts at 2 and it ends at 5 seconds. So the difference here is just 3 seconds. My acceleration is still 2. My time here is 3 seconds. The square there is part of the function. So if you do all this correctly, you should get a value of 21 meters. Well, I want to carry my work down. 21 meters gets substituted in for delta x. So therefore, my average velocity is just 21 meters divided by 3 seconds, which reduces down to 7 meters per second. It includes the direction because, again, velocity is a vector. Okay. Graphically, it looks like this. On the graph, the black dashed line represents from 2 to 5 seconds. I kind of approximate 5 seconds there in the middle. So that is 3 seconds there. Okay, and then you got to go up to the graph. That is a distance of 21 meters. Well, here it asks us to find average velocity. So if you connect the 2 points using a straight line, that slope there is your average velocity. So here the average velocity is your slope, which is 7 meters per second. Here I left out the direction because I'm just talking about the slope of the line here. Okay, but properly average velocity would be 7 meters per second east. All right, so that's part E. Now if you want to do the part E using the strategy that I do like, again, using the different velocities at the different time, you can just add it up. Okay, here VF plus VI divided by 2, and I want to run all these points again on the screen. Well, you have to be careful. Here it starts at 2 and it ends at 5. So if you kept up with how I added all these values by just adding 2 because acceleration is 2, you get 0, 2, 4, 6, 8, 10. But I'm going to highlight the 2 points that I need, which is 2 seconds and 5 seconds. At 2 seconds, it's already moving at a rate of 4 meters per second. At 5 seconds, it's moving at a rate of 10 meters per second. So I did not cancel VI out here for this one because VI does not start at 0. It starts at 2. So therefore, my VF here is going to be 10 from the data that I have here. And VI is 4. 10 plus 4 is 14. 14 divided by 2, which is 7. So you get the same answer, which I think is a lot quicker. So average velocity here is 7 meters per second, and that is east. Okay. So the slope here, again, we already know from the previous work, it is 7 meters per second. All right, let's do part F. Part F asks us to find the average speed, which is slightly different than average velocity. But here in the diagram, the object is moving one way to the right. So really, the magnitude of your average velocity, the number, is your average speed. Average speed is the same as average velocity if you're moving one way. One has the direction, one doesn't. But the number itself doesn't change. The magnitude is the same. All right, so here it starts at 4 to 10 seconds. Here, I just wrote out the fundamental average speed is equal to distance over time. But here, I know my distance is the same as my displacement. Okay, the value I'm talking about. Time is 6 seconds, from 4 to 10 is 6. So pretty much the same work as the other couple parts. I can use my displacement function because I know the value is the same as d. Here, VIT plus 1/2 AT squared. I didn't cross out VI because VI is not 0. It starts at 4 seconds. At 4 seconds, the object is already moving at a rate of 8 meters per second. So I plug in VI as 8 meters per second. Time here is 6 because from 4 to 10 is 6. And then the rest of the work is just plug and chug. Again, time here is 6 to the right as well. And then I want to cancel the 1/2 and the 2 out for this particular problem. So therefore, 8 times 6 is 48. And then 6 squared is 36. And if we add all those values up, we should get a value of 84 meters. And then 84 is going to go for distance, okay? And then average speed is going to get carried down here. So therefore, average speed is just 84 meters divided by 6 seconds, which gives us a value of 14 meters per second. And that's your answer. No direction needed because this is a scalar quantity. So on the graph, we went from 4 to 10. And then if you want, you could have used the value that we calculated for 4 seconds way back at the beginning of the video. And then here are your values, is 84. And then if you connect the 2 dots, that slope there is your average speed as well. And your average speed in this case is 14 meters per second. And the slope here again can represent your average velocity because the object is moving one way. So the magnitude of your average velocity is the same as your average speed, except one has the direction, one does not. This one, average speed, scalar, leave the direction out. All right. So here on the bottom right of the screen, I put scalar equals no direction. So as you practice, know when things have the same magnitude, know when things don't. This object's moving one way, so everything pretty much is the same value because it hasn't turned around. All right. Part F, if you want, you can utilize the strategy I used earlier. Here, I use the absolute value of my V average, which is VF plus VI. The magnitude of V average is just your speed. I've skipped a few things, so I'm just going to use V at 4 seconds and then V at 10 seconds. Okay, so I left out a few of the beginning values. All right, so if you do that at 4 seconds, your velocity is at 8 meters per second. At 10 seconds, your velocity is at 12 meters per second. That's because acceleration is 2 meters per second square. So if you plug values in, 20 plus 8 is 28. 28 divided by 2, which is 14 meters per second. And that answer is the same as the previous strategy. So hopefully you like this one. If you like it, like I said, adopt it. If not, ignore it. All right, part G is pretty straightforward, pretty whack. It asks us to find the change in velocity between 3.3 to 7.8 seconds. Well, change in velocity, that's pretty whack, okay? We can just apply the average acceleration is equal to delta V over delta T. Here it asks us to find the change in velocity, so I don't need to break delta V up. I want to keep delta V the way it is, okay, in its condensed form. All right, so to get delta V by itself, multiply both sides by delta T to get rid of the denominator. So therefore, delta V is just A times delta T. I know A is 2. Delta T in this case is 4.5 because 7.8 minus 3.3 is 4.5, okay? And then you just multiply, so therefore delta V is just 9 meters per second. 2 times 4.5 is 9. And then this is delta V, or change in velocity, so therefore I include the direction for you. So the change in velocity between 3.3 to 7.8 seconds is just 9 meters per second east. And that is that, okay? I hope that helps. Stay nerdy, don't be whack.